So given these three charges, 2 coulombs, 4 coulombs, and -3 coulombs, all spaced half a meter apart from each other, we want to know what is the electric force on object C. Which means if we're specifically looking for the force on C, are we treating C as a test object or as the source charge?
You wouldn't include C, right?
Yeah, when we're trying to find the electric
it would be the
field,
source.
We're treating A and B as the sources creating some electric field. And then C would be the test object that's experiencing that the force from that electric field. So our general
C would be
what was that?
C would be the test charge then?
Yeah.
Okay.
Test charge or test object. And it's not really like that means a different type of charge. It's just there's a bunch of charged objects exerting forces on each other. But we treat one of them as the test charge in the sense that we're trying to figure out what's happening to that object. And everything else we treat as the source charge or source charges in the sense that we're thinking of those as creating some effect on the test object. So the general scheme here is we take these source charges, those create an electric field, and that electric field creates a force on the test charge. And we're going to do this one step at a time. First, we're going to ignore the test charge entirely and just treat the source charges, A and B, as creating an electric field at location C. We're treating C as just an empty point in space for now. So I'm just going to make a note over here that charge C is -3 coulombs. And for now, we're going to be ignoring charge C. We're just going to treat C as this empty location in space. This is just location C. We're going to start by finding the electric field at location C. And then once we find that electric field, we can use that to find the force on particle C. But first of all, for the electric field, if we take a look at each source charge individually, like let's say charge B. Charge B is going to create an electric field at location C in which direction?
To the right?
Yeah. Charge B creates electric field directly to the right. So this would be the electric field contribution from B. Because a positive source charge creates electric field pointing outwards in all directions. At this location, outwards from B would be to the right. And we could even figure out how strong that is using what formula?
Would you use like the vector magnitude thing?
Yeah, if we want the magnitude of the electric field vector, what's the usual formula for that? If we're talking about
the magnitude cosine x and then magnitude sine x.
Well, we don't know what the magnitude is yet. We want to know what the magnitude is before we can split it up into components. Do you have a formula for just magnitude of the electric field from a tiny piece of charge?
I'm sure there is one, I just don't remember it.
Well, what do you think it should depend on? Like if this charge is creating an electric field, what is it about it that's going to determine how strong the electric field is?
Would it be the charge of B?
Yeah, the charge of the source, the amount of source charge influences it. So, and the more charge there is, the stronger the electric field is. So we're going to have charge in the numerator. And I'm going to write this in absolute value because we don't really care whether it's positive or negative here. We just care about how strong it is. We're going to look at the direction. I mean, we already know the direction. We're just looking for how strong it is. What else other than the amount of charge is going to influence the electric field here?
The distance?
Yeah, the distance.
Between them?
Would you expect more distance to being stronger or weaker?
If there's the distance is greater than the, it would be smaller, weaker.
Yeah, so we should put that in the denominator. We usually call this R for radius because it's a radial distance outwards from the source. And it turns out to get this to work out right, to get the geometry to work, this needs to be radius squared. And this almost is enough. I mean, this is all this stuff that influences the strength. The only thing left is a constant multiplier to make the units work out right. And that's called K, the universal electrical constant. So this formula will tell us the strength of the electric field at some distance from a piece of charge, specifically what we call a point charge, a charge that is so small in terms of volume. I mean, it might be a lot of charge, but it's packed into such a small space, we can treat it as a single point. So we can use that for this one. We got, for B, we have, ignoring direction, just looking at magnitude, we've got K times 4 coulombs divided by half a meter squared. Half a meter squared would be a fourth of a meter, and dividing by a fourth is the same as multiplying by 4. So 4 times 4 becomes 16 coulomb meters squared times K. And K has a value. K is a numerical constant. But I would just leave it in terms of K and then maybe multiply by K at the very end. Because it's going to be easier to work with 16K than whatever K actually is. So we can just call this 16K with units of coulomb meters squared. Or coulombs per meter squared. So that would be the electric field caused by B alone at location C. Any questions on that so far? And what else is creating an electric field at location C?
A.
Yeah, A is also creating an electric field here. So we're going to need to figure out what that is as well. We can use the same formula. Electric field from A, because that's just a point charge, is K times its charge, 2 coulombs, divided by the distance, still half a meter, squared. 2 divided by 1/4 is going to be 8, so we get 8K coulombs per square meter. Also, which direction would you expect that to be in?
That would go like southeast.
Yeah.
Like down
It would
to.
still be directly outwards from A.
Mm-hmm.
It's just going to be half as strong because it's half as much charge. So this would be EA, which is 8K coulomb meters squared. So we now have the electric field contributions from each of those. Now, what do we do with those contributions to figure out the total electric field at that point?
Vector algebra, I think.
Yeah, because the electric fields combine with addition. If you got several sources trying to create electric field at the same location, those vectors just add together. And this is very much very similar in some ways to interference of waves. If you've got several sources creating waves, all trying to create waves at the same point, you can just take the y values of all those waves and add them together to get the actual value of the wave at that point. So electric fields do the same thing. They add together when they're being caused by multiple sources. So the net electric field is going to be, net electric field at location C is going to be the electric field that A causes at location C plus the electric field that B causes at location C. Can we just add 8K plus 16K here?
No, you can't.
Because?
Because they're not like, they have different components. You have to add like the components separately.
Yeah, if these vectors are in different directions, we got to split it up into components. You could add the magnitudes if they were pointing in the same direction. Like if you have 16K in this direction plus 8K in this direction, you get a total of 16 plus 8 would be 24K in the same direction. But that's only if the vectors are parallel, if they're in the same direction already. In different directions, you could look at this geometrically as adding them head to tail. We've got EB plus EA. So the actual total, the electric field would be, we should expect that to be something like this. The actual electric field at location C is going to look like this vector here. but we can be more specific numerically by splitting them into components. So let's try that. EB, fortunately, is purely to the right. So we can just use the standard XY coordinates. What would be the components of EB in terms of X and Y?
It would be, well, the Y would be 0, and then would it just be the absolute value of EB?
Yeah, the magnitude itself becomes.
Oh, so 16.
Yeah, so that's just 16. I think we should really say 16K, but we could factor out the K and just say 16.0K times Coulomb meters squared. EA, though, we're actually going to have to split up. Do we know anything about the angles involved in EA? Or the angles anywhere else here?
Yeah, since all the distances between them are the same, then all the angles in the triangle are 60 degrees.
Yeah, this is just a 60, 60, 60 equilateral triangle. And by reflection, we can say that since this is just a continuation of this line and EB is a continuation of this horizontal, this is also 60 degrees. So we can say for sure, thanks to geometry, that electric field A makes a 60-degree angle with the horizontal. Or below the horizontal. And we want to split this into an X component and a Y component. X component and Y component with a right angle. EAX, EAY. And we know the magnitude is 8K. Or let's just say 8. We can multiply it by K afterwards. So how do we find these side lengths?
Would the X component be 8 cosine 60? And then the Y component would be 8 sine 50 or 60.
And we got to be careful about
negative?
Positive and negative. Yeah, since this is downwards, we treat that as negative.
Mm-hmm.
Another way you could do that, by the way, since this is clockwise from the axis instead of counterclockwise, you could treat this angle as negative 60 degrees. Cosine of negative 60 degrees will give you a positive result, as it should. And sine of negative 60 will automatically become negative, which is exactly what we expect. Or you could just treat it as 60 degrees as an absolute value in this right triangle and then fill in any positives or negatives manually afterwards. Also, cosine of 60, I'm pretty sure is just 1/2. So that's just going to be 8 times 1/2, so that's 4. Sine 60, I think, is root 3 over 2. So that's root 3 times 8 over 2. That's root 3 times 4 with a negative. And of course, these are also multiplied by K as well. So that gives us components for EA. We can say EA is X component 4K, Y component negative 4 root 3K. And we can factor out the K also. And then units still coulombs per meter squared. And then EB, we already found, is just 16,0 times the electrical constant Coulomb meters squared. So we've got the components of both of these. Now what can we do to add these up now that we've got it in components? What's the whole point of converting these into components in the first place?
So that you could find the total?
Yeah, we want to find the total electric field, E net. And by splitting it into components, we can just add one component at a time. X component plus X component, that's 4 plus 16 or 20. Y component plus Y component, negative 4 root 3 plus 0 is negative 4 root 3. And we still have a times K on the outside and units of coulombs per meter squared. So there's our net electric field as a XY component form. We know that we now can ignore EA and EB individually and just say the total electric field is 20 to the right and 4 root 3. Let's actually get a digital or decimal approximation there. 4√3, about 6.9. So we've got about 20K, or exactly 20K to the right, and about 6.9K downwards. So this is our actual electric field vector. That's the electric field at location C. Also, we've got X and Y components. It's also going to be useful to write that as magnitude and direction. How could we use this to find the magnitude? If we know the X and Y components.
Could you do a Pythagorean theorem?
Yeah, that'll work fine. And the K we can basically just treat as a unit of measurement. We're going to be squaring the K, combining it to K squared, and then taking the square root anyway. So I'm going to ignore that K for now. We can also ignore the negative on the 6.9 because it's going to be squared anyway. And we get square root of 20 squared plus that value squared, about 21.2. And that still has a K attached to it. And units of coulomb meters squared. So that's the magnitude. And what about direction? How do we find the angle this makes with the axis? If we know this is a right angle, this is a right triangle here. We've got the opposite side and the adjacent side. How would we find this missing?
Oh, tangent?
Yeah. We could say tangent of theta is opposite over adjacent. So we just take the inverse tangent of opposite over adjacent. Negative 6.9 divided by 20. And let's see what that is. Inverse tangent, 6.9 over 20, about negative 19 degrees. The negative just signifying below the, or clockwise from the axis. And you got to be careful with inverse tangent. Negative 19 degrees might actually mean negative 19 degrees, or it might mean flipped around 180 degrees. But negative 19 degrees looks like the correct angle we're looking for. So I would trust that. So there's our electric field. The electric field is 21.2 K at a direction of 19 degrees below the axis. Any questions on that electric field that we just found?
Well, that makes a lot more sense than the way I did it.
I have a question.
Mm-hmm.
So what were you saying about the two different angles that it might mean?
Oh, then in general, inverse tangents can't tell the difference between, like here we were using 20 to the right and 6.9 downward. So that's negative 6.9 over 20. If we had instead been at 20 to the left and 6.9 upwards, we'd still have negative 6.9 over 20. So inverse tangent can't tell the difference between down and to the right versus up and to the left. Or likewise, up and to the right versus down and to the left. So inverse tangents, as far as the calculator can tell, this ratio could have been from this direction or from the exact opposite direction. It just gives you one of those two values. So anytime you're dealing with inverse tangent, I would recommend sketch out what direction you expect the result to be in. When you get a number of degrees from the calculator, check to make sure that angle actually matches the direction you expect. If it's at least pretty close, that's probably it. If the direction it gives you seems to be the exact opposite of what you expect though, then you should add 180 degrees to your result. Like if we had actually had 20 to the left, 6.9 up, let's say maybe these were both negative charges, we still get a result of negative 19 degrees, but we expect it to be this way, so we should add 180 and get 161 degrees. So be careful about direction. Actually try sketching it out each time. Any other questions on that so far? So we now have the electric field. We can say the electric field at C is 21.2 K coulomb meters squared. at an angle of -19 degrees from the x-axis. How do we convert that electric field at that empty point in space into the actual force on charge C that we've been ignoring? What's the relationship there between the force versus the electric field?
Force equals the electric field times the charge.
Right. So if we just take the electric field that we have at that empty point in space and multiply it by charge C, -3 coulombs, that'll tell us the force that charge C experiences. In terms of magnitude, we're going to take this 21.2 and multiply by what here?
Sorry, what did you say?
And we're going to take this magnitude because the electric field, ignoring the direction for the moment, the electric field has a magnitude of 21.2 K. What do we do to that magnitude to find the force? We're just going to multiply that by what?
-3.
Except not for the magnitude, because magnitude is an absolute value, so it has to be positive. The magnitude is just going to be 21.2 K times
3.
Right. Magnitude of the force is magnitude of the electric field times absolute value of the test charge. Because magnitude is absolute value for vectors. So the amount of force is going to be 21.2 times 3. So the force on C is going to be 21.2 times 3. That'll be 63.6. And coulombs makes this coulombs squared instead of just coulombs. As for the angle, though, we are multiplying by a negative charge. So what does that do to the direction of the vector?
It flips it.
Right. So the force on C is going to be the exact opposite direction. The electric field at location C is down to the right, 19 degrees from the axis. The force on C is going to be the exact opposite direction. So that'll be at an angle of, and we want to measure this as an angle, again, relative to the x-axis. And for that, we can just take our -19 degrees and add 180. So that'll be 161 degrees. In other words, we can write this as the force on C is 63.6 K coulomb squared per meter squared at an angle of 161 degrees. So that'll be the force acting on object C. And if you want to get an actual number of newtons, you could look up the value of K, the universal electrical constant, and plug that in. And that should have units of Newton meters squared over Coulomb squared. It'll cancel out the Coulomb squared and meters squared, and you'll be left with just newtons. Any questions on that?
I have a question.
Mm-hmm.
So for that other formula, why is that Q in absolute value?
This one?
Yeah.
Well, here it's not. The force is, as a vector, the force is the electric field vector times the charge, including any positives or negatives. But if we're looking at magnitude, the only thing a negative multiplier does to a vector is change the direction to exactly the opposite. If we're looking for magnitude, it doesn't matter whether we're multiplying the electric field by -3 coulombs or +3 coulombs. The result is still going to be this much force. The only difference the positive or negative makes is the direction of the force. So if we had used like a +3 coulombs charge instead, we'd still get this much force. It would just be in this direction instead of in this direction. Okay. So if you're looking for magnitude, just treat everything as absolute value.
Okay, so so for the F equals EQ, for the E, you put in the you put 20 negative 6.9. Is that what
as the components, yes. So the components of the electric field are 20K in the X direction, -6.9K in the Y direction. But you could also write that in terms of magnitude and direction. Magnitude being 21.2K from the Pythagorean theorem, and direction being negative 19 degrees from the inverse tangent.
Okay, so the way you did it was after you got the magnitude of E net, you multiplied it by the charge?
Yeah. Yeah, because there are actually a couple of ways you could proceed from there. You could leave it in XY components and multiply both components by the charge. Because if you're multiplying a vector by a scalar, you're multiplying each component by the scalar, but you're also multiplying the magnitude by the scalar. So you could say each of these get multiplied by -3, and then apply the Pythagorean theorem to find the magnitude of the force. Or you could find the magnitude of the electric field and then just multiply that by 3 to find the magnitude of the force.
Okay.
If you're multiplying a vector by 3, like let's say you've got a vector v, which has an x component and a y component. If you multiply a vector by 3, what happens to it?
It gets 3 times as long.
Right. 3 times as long. So the magnitude is 3 times as long. The direction is the same. So one way of multiplying a vector by 3 would be to just take its magnitude and multiply the magnitude by 3 and keep the same direction. Or since this is negative, reverse the direction. Alternatively, you could look at the x and y components, multiply the x component by 3, and multiply the y component by 3. And then apply the Pythagorean theorem, but you still just get 3 times the original magnitude. So it doesn't really matter which one you do first. You could take the x and y components and multiply by the scalar, and then find the new magnitude. Or you could find the magnitude of the original vector, multiply by the scalar, and that's the magnitude of the new vector. So if all you're doing is scalar multiplication, then you could do that with the x and y components or just with the magnitude. Any other questions on that so far?
Question. So when you're drawing the force vector, is it supposed to be bigger than the electric field one, or does it really matter?
Bigger doesn't really apply here because they're not really measured in the same units. The force and the electric field, we draw them as vectors, but there's not really a comparison in terms of size even possible because they're measuring different things. It's like if you're measuring, let's say you measure some mass as 5 kilograms and you measure some temperature as 500 Kelvin. Could you say that 500 kelvins is more than 5 kilograms?
No.
No, they're measuring different things, so it's not really even possible to compare them. Same idea here. The electric field is some number of newtons per coulomb. The force is some number of newtons. So they're not really comparable in the sense of saying one of them is bigger or smaller. So these aren't really drawn to scale because there is no scale to compare them anyway. They're just two arrows that we happen to be drawing on the same diagram, but there's no way to compare their actual sizes.
Okay, thank you.
Mm-hmm. And that's partly because we're not just multiplying by 3. If we were just multiplying by 3, then the result would be 3 times as long. But if we're multiplying by 3 coulombs doesn't mean 3. 3 coulombs means a certain amount of charge. So we're multiplying by a certain amount of charge that we happen to be labeling as 3, but there's nothing about that amount of charge that has a 3-ness to it. 3 is just a convenient measuring system. Any other questions on the electric field or force so far?
Where did the 161 degrees come from?
That was from flipping the -19 degrees around exactly half a rotation. Because we know from the negative charge that the force on object C is going to be exactly opposite to the direction of the electric field. The electric field is -19 degrees from the axis. To flip that around exactly half a rotation, you'd have to add 180 degrees. So -19 degrees plus 180 degrees is 161 degrees. Any other questions on that so far?
I have a question. So like when you multiply by the -3, does that negative tell you that it's like flipped from the electric field vector?
Yeah, a negative multiplier has the effect of flipping the direction of the vector. If you take the force being electric field times charge, electric field is a vector in a certain direction. If you multiply by a positive scalar, you keep the same direction, you just modify the magnitude. If you multiply by a negative scalar, you modify the magnitude and flip the direction around 180 degrees. You're inverting the direction of the vector. But the magnitude doesn't depend on the sign at all.
Right. So would you include the negative in the 63.6 with the
No,
force?
because this is the magnitude. So magnitude is treated like absolute value. It's always positive. The negative,
right.
Yeah, the only thing the negative on the charge does is flip the direction. And we've already written that in the angle here. So you wouldn't write a negative in the magnitude. Magnitude is always treated as an absolute value.
Oh, okay. That makes sense.
We're listing how strong the force is and also which direction it's pointing as two separate pieces of information.
Perfect. Thank you.
The x and y components, of course, could be positive or negative, but magnitude is always non-negative.
So you wrote force as like for the one that's the 63.6. So so I thought we had two different ones for force. One of them is as a magnitude, and I think isn't the other one just the regular force? Isn't that one as like a vector?
It is a vector. I mean, force is a certain amount of push in a certain direction. You could list that as how strong the force is and which direction it's pointing. Or you could list it as x and y components. It's the same information, just written in two different ways. And that's true of any vector, by the way, not just force. Any vector could be written as x and y components or as magnitude and direction. Just two different formats of writing the same information.
Okay, so it's never going to be like the force vector is just like a negative number, right? As magnitude.
The x and y components could be negative. The angle might be negative, but the magnitude is always going to be positive because magnitude is absolute value for vectors.
Okay, thank you.
Yeah, the magnitude is just saying how strong or how big or how fast or whatever the vector is measuring without caring about the direction at all. For example, if you're talking about velocity, if you just describe how fast an object is going, that's the magnitude of velocity. But velocity also includes which direction it's traveling. So that's, again, a magnitude and a direction.
So if the magnitude is always positive, then why is there two different formulas with one of them having the magnitude and the other one it's just like...
These are not actually two different formulas. This is the formula for relating force and electric field. This is just what happens if we take the absolute value of it. In general, if you take the magnitude of a vector, like let's say you know that you've got some vector u that happens to equal a scalar, let's say c, times another vector v. So let's say u and v are vectors and c is just some scalar, some real number. And you happen to know that vector u equals scalar c times vector v. If you want to know the magnitude or how the magnitudes are related, you're essentially taking the absolute value of both sides. The magnitude of vector u is magnitude of vector v multiplied by not just c, but specifically by the absolute value of c. Because we don't want to say that like let's say c happens to be a negative number. We wouldn't want to say that u has a negative magnitude. Magnitude should always be positive or sometimes 0. So if you know that vector u is vector v multiplied by some scalar, then the magnitude of vector u is the magnitude of vector v multiplied by the absolute value of that scalar. That's true in general for any vectors or any scalar multiplication of a vector. In fact, all this is really saying is that the scalar multiplier influences the magnitude by that amount. You multiply a vector by 5, it's now 5 times as long. You multiply a vector by -5, the result is still 5 times as long. It's just now in the opposite direction. But magnitude is absolute value for vectors.
Okay, so we wouldn't be using the one without the absolute value, right?
No, this is the definition of how electric field and force relate. This is what we're using.
I mean, like, because what if we have like a negative charge, and then wouldn't that give us like a negative force?
No, it gives you a force in the opposite direction. Forces are not positive or negative. A vector does not have a positive or negative sign. A vector has a direction. So if you have some electric field in some direction and you multiply by a negative charge, the force isn't a negative value. The force is still a vector. It's just a vector in the direction opposite to the electric field because we're multiplying by a negative scalar. But keep in mind, vectors are not numbers. Vectors are quantities with direction.
Okay, thank you.
And if you want to get some general review of vectors, I've got a worksheet on mathandcheese.org that you might find useful. Let me pull up a link to that. Actually, a couple of links I want to put in here. If you go to math.andcheese.org/P7math, and then scroll down, towards the bottom of that list, there should be a couple of worksheets, trigonometry review worksheet and introduction to vectors worksheet. Take a look at those if you need any review of trigonometry or more practice on vector addition, or just working with vectors in general. And also another one that I think you might find useful, where was it? math.andcheese.org/P7C/electricalquantities.pdf. That has just a list of these 4 big ideas: the electric field, the electric force, the electric potential or voltage, and electric potential energy, how they're related to each other, and how to convert back and forth between one and the other. So take a look at those. I think that might be some useful information or practice or review for a lot of you. Any other questions on this force or electric field so far? And then the other ones you can do in pretty much the same way. Like for instance, for object B, if you want to find the force on object B, treat B as just an empty point in space, use charge A and charge C as the sources to figure out the electric field at location B by adding those vectors together. And then once you have the electric field at location B, you can multiply it by 4 coulombs to find the force on that particle. And likewise, location A, figure out the electric field caused by B and the electric field caused by C, add those together as vectors. And then that gives you the total electric field, then multiply by the charge at A to find the force. Any other questions on that so far?
Yeah, I was just wondering, so are all the angles going to be 60 degrees or?
In this case, yeah, they'll all be either 60s or 30s, depending on which part of the triangle you're looking at. But since this is an equilateral triangle, these angles are all 60 degrees. And then if you just make some extensions here, like let's say we extend this line further. This is 60 degrees, so this will also be 60 degrees. And then these are just going to be supplementary to that, whatever adds up to 180. So that's 120 and 120. Or if you put it in a vertical for whatever reason, this is then going to be 30 because these have to add up to 90. So you can use the geometry there to figure out how the angles relate to each other. In fact, if you take a look at that mathandcheese.org/P7math page, there's also a worksheet on geometry review that you might find useful just in terms of looking into how angles relate to each other. Any other questions on that?
Sorry, so which angle would we want to plug in?
It depends on what you're trying to find. Like if you're dealing with some vector, usually what you care about is the x and y components. So usually you want to look for what angle does that vector make with the positive x-axis. And then you can take the sine of that angle that it makes with the positive x-axis to find the y component, and take the cosine to find the x component. But for instance, if you had, let's say you've got a vector pointing like this way. In fact, suppose we were dealing with something like, let's say you've got this equilateral triangle, and maybe you're dealing with this vector. Let's call that vector u. This is a 60-degree angle. But what we want to do is we want to split vector u into its x and y components. So what other angles could we figure out here? Actually, what might work even better is what if we extended this further this way? By symmetry, we know these two angles have to be the same because we've got mirror image symmetry over here. If you got something plus itself plus 60 adding up to a straight angle, what do these other two angles have to be?
$60?
Yeah, these have to be 60 as well. And now this also forms a straight angle. 60 plus 60 plus something equals 180. So this is going to have to be 60 as well. So in this triangle, you could say sine of 60 is going to tell you the opposite side, which is the hypotenuse, or sorry, the y component. Cosine of 60 tells you the adjacent side, which is the x component. So that should work out to have the same sort of proportions as the other one we were working on. Any other questions on that so far? By the way, another way you could handle this vector is if you look at the angle it makes with the positive x-axis instead. What angle would that be? If we know that this angle combines with 60 degrees to make a straight angle, what's left over for this angle?
120.
Yeah, that'll have to be 120 degrees. So we would say this is the angle that the vector makes with the positive x-axis. This is the vector's angle in standard position. If you treat this as the origin, you've got a y-axis and x-axis. The angle that the vector makes with the positive x-axis is the standard position measurement of that angle. And the nice thing about using that standardized angle, if you just always measure from the positive x-axis counterclockwise, then you can always use sine for the y component and cosine for the x component. If you take sine of 120 times the magnitude, that will tell you the y component, no further modifications needed. If you take cosine of 120 times the magnitude, that will give you the x component, no further modifications necessary. In fact, if you do that, if you're measuring from the x-axis clockwise or counterclockwise, positives and negatives will also already be built in. The cosine of 120 degrees will be a negative number, providing the negative you need for the x component. The sine of 120 degrees will be a positive number, giving you a positive y component. So if you always measure the angle from the positive x-axis, then any positive or negative signs are already built in. Any other questions on that? All right, I've got to go get ready for a meeting, but take a look over those review worksheets. Feel free to bring those into office hours or drop in tutoring if you need help with them. And email me if you have any other questions. Have a good weekend, and I'll see you next time.